Hello, this is the April 15th, 2020 lecture, and we're going to start the lecture today talking about reaction of arene diazonium salts. We left off on this topic last day. We were generating the arene diazonium salt itself, and when I ended the discussion, I was talking about the idea that we talk about the generation of a cation when N2 is lost from the aromatic ring itself, and I questioned whether it was a pure carbocation or not. For the most part, we accept it as a carbocation, and the reactivity certainly indicates or seems to indicate that it's a carbocation. But at any rate, we're going to move on and we're going to look at some of the reactions of these arene diazonium salts. And the first reaction we're going to talk about is the Sandmeyer reaction. Now, in this reaction, we generate the arene diazonium salt first, and then we react it with a copper salt of some nucleophile. So in the examples here, you can see bromide, nitrile or cyanide, and chloride in these reactions. And it is the presence of the copper salt that, for whatever reason, seems to assist in this reaction. So the reaction is typical in the sense that you treat your amine with an acid and sodium nitrite to generate the arene diazonium salt, and then you treat it with a copper nucleophile, and you replace the NH2 or the arene diazonium group with whatever the nucleophile is, in this case bromide. Now, the reason we believe it's a carbocation is because these nucleophilic species always go to the position where the NH2 was. So in this case, ortho to the chloride, meta to the methyl group, and again, once again, ortho. So this is one of the reasons that we believe this to be the case. Now, the Sandmeyer reaction is always the copper salt of some nucleophile. One of the reactions that is similar to the Sandmeyer reaction, but not quite the Sandmeyer, is the reaction of the arene diazonium salt with potassium iodide. This is a unique reaction. It's a unique reaction because we don't have many ways of putting iodide on aromatic systems. So what you do is you generate the diazonium salt using an acid and sodium nitrite. Once generated, you treat this with potassium iodide, and this puts iodide on the ring. Okay, so, and I'm just repeating down here the fact that this is an interesting reaction because we do not have methods to do this normally. Okay, I'm going to move on now. Another reaction of the arene diazonium system is that you can replace the NH2 group with a hydroxyl group or OH. In this reaction, once again, you generate the diazonium salt. You treat it with copper 2+ and water, which is thought to generate copper oxide. And during the course of this reaction, the N2 is lost and an OH replaces that N2. So nothing really too amazing there. And once again, one could argue for a carbocation intermediate. Okay, in this next reaction, what we're going to do is we're going to remove the diazonium group and replace it with a hydrogen. And it's this reaction that is confusing because the reagent we're going to use is hypophosphorus acid, H3PO2. And this is a Bronsted acid. It releases H+. And yet, in this case, we're going to get a reaction where this NH2 group is going to be replaced with H. And in fact, it looks like a hydride, H-, but it's unlikely that that's occurring. So once again, you generate the diazonium salt, you treat it with this hypophosphorus acid, and we get the replacement of that group with a hydrogen. And it's this reaction that's one of the reasons that we're questioning whether it's a pure carbocation or not. Now, one of the really cool reactions of diazo groups is the fact that they are electrophilic. Obviously, they're a positive charge, so they're going to be electrophilic. But if you treat them with electron-rich amines, what can happen is you can get aromatic substitution, and you generate an extended conjugated system. So shown down here is an arene diazonium salt reacting with this NN-dimethyl aniline. And you can see that I've shown a typical electrophilic aromatic substitution where our electrophile is now N2. This generates this non-aromatic intermediate, but chloride, which is present from the salt here, will pull this proton off, re-aromatize this ring, and give us our NN-dimethylamine back, and it generates this rather large species. And you can see that this species is fully conjugated, and this is a brightly colored material. In fact, it's called butter yellow. Okay, and it's this material that became some of the first commercial dyes that were used. This was an important idea because before this time, all of the textiles that were available were natural colored. Whatever the color of the textile that was generated, that is the color it was going to be. But now we had a way of adding color to clothing, so life became more colorful. But anyway, this is butter yellow. Actually, a funny story about butter yellow is I got my PhD at University of Alberta, and the colors there are kind of a gold and green color. And they built a new athletic complex, I don't know, back in the 80s, I guess it was state of the art at that time. And for whatever reason, they thought they would color it yellow, kind of like the idea of the school color of yellow. It wasn't. It was a very bright yellow. In fact, I think you can still see it if you look at Google World and you go to Edmonton, Alberta, University of Alberta, you can see this bright yellow thing. So to this day, as far as I know on campus, it's called the Butter Dome, and it just kind of looks like a big stick of butter in the middle of the campus. Anyway, weird things, sorry. The next thing we're going to talk about is other diazo salts and diazo dyes. They're brightly colored and they're part of the textile industry. Things you might have seen: methyl orange. This is red at pH 3.1 and lower, and yellow at pH 4.4 and higher. Not the best indicating dye in the world, because the switch from red to yellow is sometimes very subtle and difficult to see, but it is methyl orange. And one that you are familiar with, Congo red. This is the Congo red litmus paper that you guys use in the lab. Below pH 3, it's that deep blue violet color, and above pH 5, it's that deep red color. So this is something that you've actually seen as a diazo dye. Moving on with reactions of amines. Amines and sulfonyl chlorides. If you guys hadn't been affected by the COVID-19 situation, you would have used this type of reaction in what is called the Hinsberg test in the lab to identify whether your amine is a primary, secondary, or tertiary amine. And you react your amine with sulfonyl chloride, and this creates a sulfonamide material and HCl. And it is the reactivity of these sulfonamides that allows you to determine whether it is a primary, secondary, or tertiary amine. And obviously tertiary amines are not going to react with sulfonyl amides at all. Okay, so now we're going to move on and we're going to look at another use of sulfonamides. And this is actually probably a little bit more important than the Hinsberg test. The sulfonamides were euphemistically called sulfa drugs, and these were some of the first antibiotics that were used in medicine. A gentleman named Gerhard Dogma, I don't know how to pronounce this individual's last name, received a Nobel Prize in 1939. He worked in a chemical plant, and they were looking for antibacterial materials. But at any rate, his daughter had a bacterial infection. She was diagnosed that she was going to die. And he gave her Prontosil. Prontosil is shown here in the notes. And what happened was his daughter ended up recovering from the material. So these sulfa drugs were some of the first antibiotics that were used of their time. It turned out that Prontosil was not the active form of the material. What happened was when you gave this material to a human, it broke down and it creates this sulfa-anylamide. And this material in and of itself is a little too toxic for direct use. So the fact that you gave somebody Pronicil that allowed it to break down slowly was probably the thing that saved his daughter's life, that she wasn't poisoned by the material. But anyway, at any rate, these were some of the first antibiotics of their time. The bacteria developed fairly quickly to inhibit their biological activity, but at any rate, this was some of the first antibiotics. Moving on from there, Hoffman elimination. You can use amines as leaving groups. Now, they're not going to be good leaving groups because they're pretty basic materials. However, if you alkylate or over-alkylate the amine and generate the quaternary ammonium salt, now suddenly the amine is a good leaving group. So the first step of this reaction is going to involve exhaustive methylation of the NH2. This is going to generate the quaternary ammonium salt. So 3 equivalents of the methyl iodide reacted to generate this species. Now you treat this with silver oxide and water. What's going to happen is the silver is going to precipitate away the iodide, and you're going to generate some hydroxide, which will eliminate the material. This reaction is generally thought to be an E2 type reaction. Fun memories from last semester. Okay. Now we're going to flash back in time just a little bit. We're going to look back at some material from chapter 12. At the time that we talked about chapter 12, I said that we would be going back to this at some time. That time is now. Polymers. Polymers are incredibly important to our everyday life. Look around you. If you removed all the materials that were around you at this moment, chances are you would probably be fairly unclothed. A lot of the material that you're sitting on or furniture and things that are around you would be missing. So the idea of the development of polymers was very important, incredibly important in terms of safety materials and stuff. You know, if people are in car accidents now, you kind of expect them to survive. If they don't, you believe that it must have been a truly horrific accident. But at any rate, polymers are important for our economy and important for the world economy. There are 2 main types of polymers. There's chain growth or addition polymers, and these are involve the use of alkenes. And then there's condensation or step growth polymers, and this is usually the reaction of 2 molecules with the loss of a small molecule like water or alcohol of some sort. We're going to talk about chain growth polymers first. And there are a number of ways to initiate these reactions, and they're pretty typical in the sense that the first one is a radical, and then what will happen is the radical will react with one equivalent of the alkene, and then this generates a new radical which will react with another, and you can just subsequently continue the reaction in this manner. All of them are going to occur in the same way. We can start the reaction with cations, and of course this continually generates more cations. Or you can start the reaction using an anionic method, so just a nucleophile, for example. And again, the ideas are the same. Now, these reactions are important. One of the main polymers that are generated in this way is polyvinyl chloride, PVC. So this is simply ethylene has a chloro group on it. You react this via a radical mechanism and you generate this polymeric material. You would have probably seen PVC primarily in pipes in your home, unless you live in a very, very old home. And CDs and polyvinyl chloride is used for plastic raincoats, shower curtains, garden hoses, all sorts of things. So it's all around us. Another type of polymer is Orlon. Again, ethylene starting material, but in this case, there's a nitrile group attached. The reaction is initiated obviously by a radical mechanism because we use peroxide. Ferric sulfite is also used, and this generates this type of polymer. This is a fibrous polymer, and so it's used primarily in carpets and other pretty hard-wearing fabrics. And last but not least, Teflon, tetrafluoroethylene, react with iron and peroxide, again a radical initiation, and it creates this tetrafluoropolymer. Now, this polymer has a very high melting point and there's a very low coefficient of friction. That is, not much sticks to it. And the development of Teflon is a really interesting story. Some researchers were using tetrafluoroethylene for some reaction, and they kept using these cylinders of this material, and they really felt that they weren't not getting all of the gas out that should have been there. And so they weighed the cylinder prior to what they were doing, and then they weighed it afterwards, and they found that indeed there was not as much gas as the gas company said that was in there. So what they ended up doing is cutting open a cylinder, and in the inside they had found this polymeric material, which was Teflon. And that was the start of the story of Teflon. Of course, Teflon is used to line pans, so it creates a non-stick surface. It's a really cool idea, but the really cool part of this is not the discovery of Teflon itself, it's how they got Teflon to stick to the pans. And there is a book out there that kind of describes that story. It's a pretty fascinating read. At any rate, I'm going to leave you here today. Everybody have a good day, and we'll see you next time.